Volcanoes, they're hot, they're explosive, and in some cases it pays to be prepared for them. But while we can sometimes predict when one of these geological wonders will blow its top, the truth is that there's so much about volcanoes that we still don't understand. So let's learn more about the science behind these fire and brimstone factories to help us better understand their beauty and danger. Volcanoes come in many shapes, sizes, and styles, but all of them have one thing in common: they're awesome. And like other natural wonders, they were formed by forces beyond our control. But what exactly happens under the Earth's surface to cause these awe-inspiring geologic marvels to erupt? To answer this question, let's take a look at what lies beneath the surface. The Earth's core is a ball of superheated metal so hot that its temperature reaches 9,800 degrees Fahrenheit, or around 5,400 degrees Celsius. This region, which begins around 2,900 miles, or 4,700 kilometers below our feet, is surrounded by the Earth's mantle, a mostly solid layer of rock that extends another 1,800 miles or 3,000 kilometers upward. Though technically a part of the mantle, we also have the lithosphere, which is the Earth's crust plus the uppermost part of the mantle, which together behave as a rigid unit. Now, even though the lithosphere is called a sphere, it's not round like a basketball. Instead, it's broken up into numerous pieces called tectonic plates that are in constant motion. And that's why we have earthquakes, mountain ranges, and yes, volcanoes. Now within the mantle, temperatures reach around 3,700 degrees Fahrenheit, or 2,000 degrees Celsius. That's hot enough to turn some of the rock into a very viscous liquid called magma. In fact, as the plates carrying the lithosphere slowly move atop the mantle, they sometimes move apart, allowing even more magma to bubble up toward the surface. And when it reaches the lithosphere, it can start to pool up in the cracks and weak spots. As it continues to rise, the pressure from the weight of the overlying rock squeezes most of the gas bubbles out of the magma, making it even more viscous. Eventually it cools enough to solidify into igneous rock, creating vast outpourings of black or gray-colored rock. We call these places where magma collects below the surface a magma chamber. And over time, this underground chamber can grow quite large. But just how big can a magma chamber get? Well, the largest known magma chamber ever discovered is located beneath the Yellowstone supervolcano. It's so massive that scientists estimate it could hold over 1 trillion gallons or 3.8 trillion liters of molten rock. And if that doesn't sound like a lot, consider this. The total volume of all the water in all the swimming pools in the United States is only about 65 billion gallons, or 245 billion liters. So the magma chamber beneath Yellowstone could hold over 15 times that amount of molten rock. But before we get too excited about taking a dip in a sea of lava, let's talk about why magma chambers are dangerous. You see, the surface of the Earth isn't always as stable as it seems. In fact, the thin veneer of dry land we call home is crisscrossed by a network of faults which are fractures in the rocks, and sometimes these faults can become the pathways for magma to escape from a magma chamber. When that happens, we call it a volcanic eruption. In fact, the most powerful eruptions in history have been caused by magma bursting through a fault line. For example, the 1815 eruption of Mount Tambora in Indonesia was so violent that it literally blew the top off the mountain. In fact, its eruption column rose 40 miles or 65 kilometers into the atmosphere, leaving behind a caldera nearly 2 miles or 3 kilometers wide. And while the scenes of flowing rivers of lava might seem like something straight out of a movie, they're actually pretty rare when it comes to volcanic eruptions. Most are actually what we call explosive eruptions. You see, as magma makes its way toward the surface, it brings gases with it, including water vapor, carbon dioxide, sulfur dioxide, and hydrogen sulfide. And as the magma approaches the surface, the pressure drops dramatically, causing these dissolved gases to expand rapidly into bubbles. Because of this sudden change in pressure, the viscosity of the magma causes the bubbles to collapse, releasing energy that blasts rock and ash into the air. It's this buildup of pressure that eventually leads to an explosive eruption. Now, the type of material ejected during an explosive eruption depends on the magma's silica content. If the magma has a high silica content, it'll form thick, sticky lava that piles up around the volcano. On the other hand, low silica magma is more fluid and creates runny lava that travels long distances away from the volcano. And while low silica eruptions tend to be more explosive, high silica eruptions can pose their own unique challenges. For example, when Mount St. Helens erupted in 1980, it sent a pyroclastic flow down its slopes. Pyroclastic flows are incredibly hot mixtures of gas, ash, and rock that travel at high speeds. And because they're so hot, they can literally burn forests to ash in seconds. Though perhaps no volcanic eruption in history is more famous than the eruption of Mount Vesuvius in 79 AD, which buried the prosperous Roman city of Pompeii in ash. So explosive was this eruption that even today archaeologists continue to uncover new artifacts from the event. But no matter the type of eruption, all volcanic eruptions are dangerous. And in the past, humans have suffered greatly due to their destructive power. For example, the 1315 eruption of Mount Elgy, Bulgaria was so massive that it wiped out entire villages and killed thousands of people. In fact, it was so catastrophic that some historians believe it may have contributed to the Black Death pandemic of the 14th century. But in spite of their danger, humans have often settled near volcanoes. For example, the fertile soil surrounding Mount Vesuvius made it an ideal place for the Romans to build a city. And today people live and work near volcanoes all over the world. In fact, Mount Vesuvius is still an active volcano and millions of people live within its blast radius. Because of this, scientists have been working hard to improve our ability to monitor and predict volcanic activity. For example, in the early 1980s, scientists began using seismometers to listen for rumblings beneath the surface of Mount St. Helens. These instruments, which are used to detect earthquakes, have helped scientists identify the first signs of an impending eruption. They've also used satellite imagery to track changes in the shape of the volcano, as well as gas emissions and ground deformation to identify areas of unrest. And it's thanks to these efforts that, for the first time in history, we were able to issue an accurate warning before the 1980 eruption of Mount St. Helens, giving local residents a chance to evacuate before the eruption. But even with all our technology, predicting volcanic eruptions is still difficult. For example, in 1985, a series of earthquakes beneath the Colombian volcano Nevado del Ruiz raised the alert level to 3 on a scale of 4, indicating that an eruption was possible, but not imminent. However, a few months later, a magnitude 5 earthquake struck, and mudslides on the volcano's flanks caused lahars, fast-moving avalanches of mud and debris that swept through nearby towns, killing over 20,000 people. Because of tragedies like this one, scientists have been working hard to develop better ways to monitor volcanoes and issue more accurate warnings. For example, in the years since the 1980 eruption of Mount St. Helens, scientists have developed instruments that can measure even the smallest changes in the volcano's shape, allowing them to detect the earliest signs of an impending eruption. They've also developed new methods for tracking gas emissions and ground deformation, which can indicate that magma is moving beneath the surface. And these efforts have paid off. In 2011, for example, scientists were able to accurately predict the eruption of Mount Etna in Italy, giving local residents time to evacuate before the eruption. But while we may never be able to completely predict volcanic eruptions, we can take steps to mitigate their impact. For example, in the years since the 1985 eruption of Nevado del Ruiz, scientists have developed new methods for tracking lahars, which can give people living near volcanoes more time to evacuate. They've also developed early warning systems for explosive eruptions, which can give people time to take cover. Because of these efforts, we may never be able to prevent volcanic eruptions, but we can make sure that they don't take lives. So the next time you hear about a volcanic eruption, take a moment to appreciate the incredible forces that shaped our planet and the incredible work of scientists who work tirelessly to keep us safe. Speaking of incredible forces, did you know that your support helps us produce these videos? Our supporters also get access to a ton of cool perks like blooper reels, behind the scenes fun and more. So if you want to support us and get some cool perks, click the link below. And thank you for watching.